can you get started learning, building, and earning with Near? And I'll review this again at the end of the presentation, but I just want to give you a sense of what opportunities exist for developers that want to come and learn with Near. So we have several of them in play, and there is real support behind this, real funding, people who are paying attention, who want your every success. And so, quite an opportunity. As you may have noticed, this year has been a massive resurgence in the blockchain space with many new developers coming, maybe the most since 2017 and kind of the big uptick there in the market. But things seem to be different now. We're focused on quality, scalability, and some real new innovation in the space. So it's quite an exciting time, actually. And because of that, we have launched this Open Web Collective, where in 2020, many teams working on new projects, many teams working on new projects raised a total of $15 million US for their projects, different kinds of funding, angel funding and seed rounds and so on, to basically support their development on the decentralized web. So that's quite exciting, and I'll share a URL with you a little bit later about how you can apply for that program yourself if you're interested. We also have a grants program with a significant budget behind it, where we're basically funding key projects by the community for the community. If you have an idea, something you want to build, some enhancement, maybe a new wallet you want to develop, or some new utility or tool, or maybe some new feature of the platform, then you can make that proposal and get it reviewed and potentially win a grant to actually get that time and effort compensated, depending on how much work you want to do, of course. You might even decide to build a team around it, whether you go solo or in group. That would be entirely up to you. So there's a grants program. There's also a bounties program. And this bounties program is a little bit different from the grants in that these are basically our ideas, features that we're aware of. Of course, some of the suggestions come from the community, but these are things that are sort of clear and present targets in the area of development that we're looking for. So the bounties program, we might have a meeting internally to the Near Collective, and someone might say, hey, why don't we do this? And someone might say, why don't we write a bounty for that? And then we'll expose that publicly. And so these are opportunities to earn tokens and fiat currency for the development of these projects, typically smaller in scope. And then finally, there's this Figment Learn pathway for Near, a fantastic opportunity to get to know Near as a developer and actually learn while you get paid for that. So there's a 10 Near compensation as incentive to complete this tutorial. Doesn't take very long at all, actually. And the reviews are quite good. So maybe 90%, 95% of the feedback that we're getting is 5 out of 5 on the quality. People seem to enjoy it very much. It goes right into the software. So this isn't for the faint of heart. You're going to start writing code and submitting transactions to the network within a few minutes of starting the tutorial. So again, happy to share links there. And then finally, we have Gitcoin Kernel, an 8-week fellowship that is launching. And this is another opportunity to learn with some of the best. So if you're interested, you can check that out as well. A little bit later today, we're going to have a workshop where we play a scavenger hunt game. If you're not familiar with how scavenger hunts work, the idea is you look for something. And as you look for it, you might learn something, you might discover something new. And then at the end, we'll be rewarding people with Near swag, things like t-shirts and so on that you might like to show off to friends and family. So here, the skills that are required actually very simple. If you're interested in Near, you have an attention to detail and some patience with yourself while you go through and do the work. You'll find out that the scavenger hunt can actually be a lot of fun, a great way to learn. And so we'll be diving into the internals there, going through some of the details of Near and conceptual overview. And these are some of the things that we'll be rewarding there. I see Shreyas has made a comment. Hey, Shreyas. Yeah, we would love to have you join us there for the scavenger hunt. Agreed. Okay, so let's talk about near from the web developer's perspective. So web 1, you could say, well, let's start with web 0. 1960s, 70s Xerox PARC, the development of networked computers, TCP/IP, things like that. So fast forward a couple of decades later, mid 90s, we have web 1, where basically we can broadcast information as individuals and businesses. A website for a restaurant menu, or some hyperlink documentation, or whatever, an index in a search engine that you can use to discover some of this information, but not much of this back and forth. Web 2, then, the social web, where we as individuals can have our own TV stations on YouTube. We have our own Instagram accounts with potentially hundreds of thousands or millions of followers, and we start participating actively in the Web 2. That's the web we're living in now. And Web 3 is the promise of this new place, this space where we have not only the ability to share and engage with one another, but we actually control the information. YouTube can't shut you down if they don't like the content that you're broadcasting, for example. So this Web3 world is quite interesting, and this is what blockchain technology promises to deliver. So here, just a handful of qualities about this this transition. If you hadn't thought about it, there are some similarities and some differences. So if you're a web developer and you're thinking about topology, of course, you've heard of client and server. With Web3 now, we involve blockchain. And that adds some new primitives like identity and money that we didn't have in Web 2, certainly not in the way that we have it in Web 3. And app development technology, it's quite similar, actually. You're very likely writing in JavaScript if you're deploying anything to the front end. But on the back end, you might have quite a complicated tech stack in Web 2, whereas in Web 3, the sort of the key differentiator there will be the smart contracts, the contracts that you're writing in Solidity, for example, if you're deploying to Ethereum, or in Rust and assembly script, which is a lot like JavaScript, TypeScript, if you're deploying contracts to Near. So in that sense, the back end, where you're controlling business rules, mission critical constraints on your application, those are written in smart contracts and deployed on Near using Rust and assembly script, Rust or assembly script. And of course, you can mix contracts written in both of those languages, have them talking to one another. From a security perspective, Web 2 and Web 3 are different in that I'm sure you're aware of this, but every time you log into Facebook, Twitter, whatever, you're actually sending your username and password to their servers, where someone then has to hash them and check the value of a hashed password in their database to see if that matches. But there is a line of code on all of these services that you and I use, where our username and password is available to be printed out to the console, sometimes by accident, into logs or what have you, as plain text. And so to solve that, we have mechanisms like OAuth, where basically some third party vouches for who we are. But again, there's still this exchange of credentials where your secrets leave your computer. They actually go across the wire to some other machine. Not so with Web 3, actually. With Web 3 and public-private key pairs, these asymmetric key pairs, you're signing your transaction locally. Maybe you don't even know what your password is. Maybe you don't know what your private key is because it's sitting on a ledger or some other hardware security module, some other hardware device. And so in that case, it's very different. You control your username and password, your security credentials, not just in theory, but in sort of a very real practical sense. You may not even know what your private key is when you're signing a transaction, and so these are some of the major differences here. When we talk about security, also in terms of services and servers, we have all the same kind of tech stack that we have. AWS, Amazon Web Services, or Google Cloud Platform, or Azure. But on top of this, we also have this network whose integrity is maintained by some consensus mechanism. So the reason that blockchain is sort of different in that it has these new qualities is really, we could talk about 3 new technologies that have come together over the last, say, 10, 15 years. Cryptography and public-private key signatures. So that's a major advancements in cryptography, where basically you can make a claim of identity. I approved this transaction or signed this transaction, and that is mathematically defensible. It cannot be faked with any available technology that we have today. Nobody can pretend to be you and sign a transaction with a key that isn't yours, and that's the cryptographic security behind this technology. So that's one of them. The second one is decentralization, and we saw that with distributed systems for sharing files like BitTorrent or Napster or whatever, depending on what your scene was. And in that sense, we have these computers that are, in far-flung reaches of the planet that are communicating together and sharing data to coordinate and make the network work in the way that you expect it to. And then the third technology is this triple ledger technology, where maybe a single ledger is the butcher remembers that you've taken some meat without paying for it last week, and if you don't pay, then they will shame you in the public square. Double ledger technology would be where two companies or maybe two countries keep a balance of accounts, and so they know who owes what, in terms of exports and imports, for example. And triple ledger technology is where you keep a record, I keep a record, and there is a record available in public view, and that's the blockchain view. So these three technologies, cryptography, decentralization, and the triple ledger, come together to make this new system. A big part of this is consensus. That's why I'm talking about it in this context, where you have to find a way for several people who are running these nodes, paying for the electricity, the hardware, the storage, and compute, can maintain the integrity of the network through some sort of incentivized program where maybe they get paid for doing that. That offsets the costs, the operating costs of running these machines. And so any consensus mechanism wants people to agree on the ground truth in the network. What data is true? Have to be compensated in some way. That's what consensus mechanisms are. And that's a completely new model that Web3 brings to the table. And so the unique selling proposition here, or the key performance of these in Web2, we're used to fast, cheap data as being native. You can move data anywhere, anytime, and you have very advanced, flexible services like Amazon S3, for example, where you can basically put anything, anytime, for as long as you want. Where in Web3, some of the new primitives would be things like the fact that it's unassailable, permanent identity and truth, as well. Then on top of that truth, we can layer trust because we believe in that truth, because it's incentivized truth, effectively. And on top of that trust, we layer things we care about, like identity, money, businesses, transactions, finance, and so on. So that's kind of the big shift. If you're coming from Web 2 as a web developer, this is the first time you're seeing anything about blockchain technology. Hopefully this gives you some framing that helps you make sense of what's happening and why this is a seismic shift, a major shift in the way people are thinking about this technology. So why near? And again, if the slides are not transitioning or you're not seeing something, please just ping me in chat here. And also a time check would be helpful. We're about 15 minutes in. If someone could help give me a sense of exactly how long I have. I didn't ask in the beginning, I should have. So near is cheaper, faster, and easier to use. And I'm not going to read all of this text for you, but I'll give you a high level sense of how we're thinking about this from a development perspective. If you want to learn how to build a blockchain dApp, a decentralized app, you typically, for most layer one technologies where you would deploy your contracts, you need to learn some new technology that's specific to that system, a custom programming language, that has its own kind of quirks, with maybe some custom tooling or something like that that's been developed by that community. Whereas with Near, what we have committed to are open languages with their own robust communities. So the Rust to WASM toolchain is the most mature WASM toolchain available today, and AssemblyScript compiles to WASM and is almost, it looks exactly like JavaScript and TypeScript if you're trying to learn how to build a smart contract, but you don't want to spend a lot of time learning a new language. And so for the million JavaScript and TypeScript developers on the planet, this is a very compelling opportunity to start writing smart contracts and building dApps without having to learn any new tech, really. But you learn how to think about blockchain applications, and you learn how to express your ideas that work in dApps, decentralized dApps. without having the overhead of learning a new language, a new tooling, and so on. And of course, these languages are transferable. Ultimately, you can use Rust anywhere. So in that sense, from a development perspective, there's a very compelling story here. It is cheaper and faster and easier to get started with Near. And then in terms of production, when you deploy your application, the transactions themselves are many orders of magnitude cheaper than the status quo. Essentially, Ethereum in this sense is the only game in town. And so, if you're talking about high prices for transaction fees, if you've been doing any kind of trading over the last several months, DeFi story, that whole scene, you've probably noticed that the fees are actually quite high, and those are 10x, 100x, thousands x lower on Near, depending on the kinds of transactions that you're conducting. And of course, it's very snappy, very fast, 1 second block time with 3 second finality. So very, very quickly, you'll see that your applications respond quickly, they have a better user experience, and they're less expensive for you to use. In terms of getting started, wonderful, thanks for that private message, 30 more minutes. And so we'll certainly have time for questions. And I'm also happy to dig into some other aspects that we're not covering in the visible slides. And so how would you get started with Near? One of the simplest things you can do is visit near.dev. That's the website. And there we have about a dozen examples that you can just click through and run right from your browser, actually, using Gitpod, a web-based IDE and a Dockerized development environment. So if you want to try any one of these examples, look at their source code. Some are written in Rust, some in assembly script. You can see it in the little blue tags at the bottom, which is which. These examples are well documented and instructive for you. So that's one of the fastest ways to get started. If you want to see, like, what does a dApp even look like? How do I even use one? You're talking about less than a minute to check these out. You can also build a new application very quickly. If you're familiar with React, they have a utility called Create React App, and so based on that, we've created Create Near App, which gives you this ability at the command line to very quickly generate an application where you have a choice of the front end and contract technology. So notice I'm not saying front end and back end, I'm saying front end and contract, because the contract is effectively the enforcer of your business rules and your store of data. Although of course it is going to be slower and more expensive than a typical web-based database, or Postgres or MySQL or whatever sort of backend you want to use, MongoDB, something like that. Blockchain in general is going to be slower and more expensive to use, but you get those guarantees that we talked about earlier: trust and truth and identity and money and so on. So you get to pick this front end and contract technology, and you make these combinations in order to build some kind of quickly scaffolded application that you can then base your maybe hackathon project on, or your MVP on. And then once you've gotten a sense of how to build things, maybe done some market validation with a few users, then you can kind of rebuild or commit to cleaning up the scaffolding that we've given you to work in the way that you want it to work, to customize it. Also, we have if you're coming from Ethereum development, this simple cookbook that lets you quickly compare and contrast. If I do this in Ethereum, how would I do this in Near? And so hopefully that helps folks. There's links in the slides to that. And again, you'll have access to the slides after this talk. This year, we released the Rainbow Bridge, which is this connection between Ethereum and Near that allows you to move at an architectural level anything from one network to the other, back and forth. But from an implementation perspective, today, what's ready and working is you can move tokens, ERC20 tokens, back and forth. But the structure itself actually allows you to move anything. And I'll talk briefly about what that looks like. We can dig deeper if anybody is curious about this specific capability, but I won't spend more than about 30 seconds or a minute on it. If you look at Near and Ethereum as two networks running together, and I'm reading from the top to the bottom now, on the far left, you can see setup, use case, and extend. So if you look at these two networks together, what we've deployed are contracts. We've deployed contracts on Ethereum written in Solidity that are a light client for Near, listening to things that happen on Near, right? Transaction headers and the progression of the Near blockchain, with something called a Near to ETH relay that is sending these transactions. Maybe it's a node program or a cron job or something that's running off chain, that's sending these headers into the smart contract that is written in Solidity running on Ethereum, paying attention to Near. It's called a light client. And the inverse is true. There's a contract written in Rust living on Near that is listening to the Ethereum network with an ETH to Near relay, sending it headers from the Ethereum network. So these two light clients allow the networks to watch one another. And then on top of those, we have this idea of a prover, which basically proves something specific about the network. The Near prover, written in Solidity, living on Ethereum, can prove that an event has occurred and been recorded on the Ethereum network. The Near prover, written in Solidity, living on Ethereum, can prove that a Near transaction outcome has been completed. Some execution has happened on the Near protocol. And the Ethereum prover, living on Near, written in Rust, can prove that an event has occurred on Ethereum. So that's the inverse relationship. The networks are watching each other, and then we're able to prove these primitive things. And then on top of that, we can build things like, say, a token locker on Ethereum, where you put in some ERC20 tokens. That gets proven on the Ethereum side. On the Near side, we mint some related fungible token, a wrapped ERC20, you can call it, on your protocol, and then issue that to your wallet, effectively transferring that ERC20 across the network. And then you can put it, kind of unlock that on the Near side and open up the tokens on the Ethereum side. So this bridge gives you the ability to move any of this data basically across these two networks. Hopefully that's clear. We can discuss it more if anybody's interested in the details, and we have some demo videos and so on. And you can actually get started working with this today. Between Ethereum and Near, again, assuming that many of you have experience with Ethereum development, we can talk about accounts, state, transactions, gas, and blocks. What are the differences here? And again, without reading all of these, I'll just point out some highlights. Ethereum, you typically talk about two kinds of accounts: externally owned accounts and contract accounts. And with Ethereum, when you make an account, effectively the account is some subset of the bytes that represent the key pair, the public key pair that you use to control that account. So any user account, externally owned account on Ethereum, has a public key and a private key. Part of the public key is used to name the account. You can only have one key to control that account. And then if you want to deploy a contract, you deploy the contract bytes to some special address in the Ethereum network, signing the transaction with your externally owned account. A new account is generated for the contract based on some hash of your account name and the nonce, number used once, how many times you've used that key. And then that account gets deployed, that contract gets deployed to Ethereum, and then you're stuck with that. If you want to redeploy a new version, something like that, you get a new account. It's a new nonce. You've used the number again a second time, and so you get a new account for the contract. So in Ethereum, you've got two accounts: externally owned accounts and contract accounts, and you don't really have very much control over these accounts and how they work. There's a lot of stuff built into Ethereum, a lot of assumptions, and these are critical from a security and safety perspective, so that you don't get people sort of replacing accounts or what have you, replacing contracts. So all that makes sense. Near takes this one step further now and says, look, why don't we simplify this with just one kind of account? We can have accounts that are human-friendly names. So if you're familiar with Ethereum ENS, it's like having ENS built in at the protocol level. And so we have these accounts that you can create, and you decide whether or not you want to deploy a contract to the account. So I have an account on Near testnet, for example, that has no contract deployed to it. It has some tokens in it, and I use it to send and receive tokens and invoke methods on contracts or dApps that I want to use. That's fine. But if I want to deploy a contract, I could do it on my account, or I could make a new account, maybe a sub account, because we have a naming system similar to DNS. So say Sherif.testnet is my account. So my dApp.Sherif.testnet might be my application. I could even have v1.mydApp.Sherif.testnet as this human-friendly name, which is an account that is some sub-account of mine, so I control it. And on this account, I could decide to deploy a contract. How do I control the account? Through public-private key pair, same technology, but with Ethereum, I can attach an unlimited number of keys to any account. And the keys are of two types. Full access lets me do anything, create the account, delete the account, send money, deploy a contract, call any methods on it, and function call access keys that are restricted to making specific calls of methods up to a certain budget. There's another trick there where I can actually set the receiver to be my contract or even another contract somewhere else, effectively paying for users to call that method on a different contract. You can think of that as being something useful that you might use for maybe a freemium model in your dApp, where you want to provide users with a limited number of calls or something up until the point where they decide they want to buy. And so there's some new flexibility there. And of course, if you want a trustless account, an account that you can guarantee nobody can control, you would delete the full access keys from that account. And that way nobody can replace the contract that's there. There's a little bit more detail there that we can discuss, because contracts can actually call other contracts and create accounts and keys. And so you'd have to look at the code in the contract to make sure that it couldn't add keys to itself. But that flexibility gives us a much easier mental model to reason about when we talk about deploying accounts, versioning contracts, managing the relationship between a family of contracts, maybe all scoped within a certain parent account. These are some major differences. And there are others there in terms of state, transaction, gas, and blocks, and so on. If we talk about connecting to Near, this is a very high level view of maybe your dApp that's connecting to Near using an API library from a JavaScript context. Near API.js is this library you can use on the client side or server side. So if you're writing in JavaScript for the browser, or you're writing in Node for the server side, you can use Near API.js. And the differences are actually quite small in your code. You'll see in just a moment. And then that wraps the RPC interface. So we send JSON over HTTP to an RPC endpoint, remote procedural call endpoint, and then that replies with JSON from the blockchain. By the way, all of our tools use exactly the same thing. So any examples that you see at near.dev, any examples that you see in terms of our own tooling, like Near Explorer and Wallet and Near CLI, all of these are also using Near API.js, and in some instances, they might talk directly to the RPC interface. And so there's quite a bit of flexibility in the way these tools work, because we use them ourselves. So that's a key point to recognize. And if we zoom in just a little bit now, your dApp using Near API.js on the far left, communicating with the blockchain layer, this is how you might actually do your work. So you would have, for example, Near API.js communicating with the blockchain to the RPC interface, and you've written contracts, maybe using one of our software development kits for assembly script Near SDK-AS, or for Rust Near SDK-RS. And these are just helpers to allow you to access, for example, the runtime context while the contract is running, or access storage, or some of our more higher level collections for working with maps or arrays or queues, and of course all the logic of your contract. So you would write your app, connect to Near with Near API.js to send and receive calls, send transactions, sign in, things like that. You would write your contract in assembly script, maybe in Rust, maybe both, as two separate contracts, and deploy them that are working and collaborating together to make your app work. And then you would deploy those into the blockchain, into an account, and the contracts. And then when you make the call, the contract spins up. So your app makes a call in step one, that sends the transaction to the blockchain layer, which then spins up the runtime layer calling apply. That brings up a virtual machine, maybe loads your contract from storage, and then does some reading and writing to storage to save state, and then sends the reply back that you receive in your dApp, and then you can show to your user, or take whatever the next step is. And so this is the kind of the part that's yours in terms of the platform. These are how things work. When we talk about connecting dApps, and by the way, feel free to ask me to slow down or stop, or if you have any questions, please post them in chat. I can see it here. So Digging in a little bit more, Near API.js is this library, a JavaScript library written in TypeScript actually, that lets you connect with Near. And these are all the features that it supports, generating key pairs and creating transactions, signing transactions and sending them to the network. And you can see some of the primitives that are exposed by Near API.js. This is the difference between the client side and the server side code. And you can see it's basically letter for letter exactly the same, except that we're referring to window in the client side, global on the server side, and for whatever reason we want to expose this object Near in the global scope. But the biggest difference in terms of where's the key store. So if you're on the client side, we use local storage scoped to your dApps URL, and if you're on the server side, we use the file system. So when we talk about writing contracts, we're going to write them in assembly script or in Rust. And of course, as I said before, you could write contracts, part of your system in assembly script and part of your system in Rust. Why would you want to do that? So the advantages of Rust is that it's a safer language. It's more mature. And so it's more suitable for any sort of applications that are handling large amounts of finance or mission critical applications where any errors or any bugs in the contract would be a serious problem. But assembly script is fantastic. If you're coming from JavaScript or TypeScript and you want a very shallow, fast learning curve, you can start writing contracts in a matter of minutes without almost any new sort of syntactic overhead of understanding what you're doing. All your thinking is focused on blockchain concepts and how Near works without any of the overhead of language and tooling and so on. So in that sense, it's a very compelling story. Great for hackathons, prototyping, MVP, getting to product market fit, and then maybe factoring out parts of your applications and writing those in Rust where they are managing high value. And of course, these contracts can communicate. So there's nothing stopping you from having both kinds of contracts living in the same dApp. Here's what they look like. So assembly script you'll see on the left. Here we're talking about contract data specifically. This is some sort of a posted message class with some attributes of whether or not it's a premium message and who the sender is and what the text of the message is. And in this case, we can check the reading on the left-hand side, the context for the attached deposit to this. And that's where money becomes a primitive. And again, the context sender, where identity becomes the primitive. You can move money around by attaching it to a function call. If you're coming from Ethereum, of course, this is obvious to you. But if you're coming from a Web 2 world, that probably seems insane. And so this is one of the most compelling aspects here of blockchain technology. Rust on the right-hand side with contract data. You can see the same structure here, but syntactically it's different, of course, because of the requirements of Rust. And so we have this struct that represents the posted message, and then we have the interface, here where we can spin up a new posted message in Rust. And then if you're talking about behavior, that was data. If you talk about behavior, here's some examples. I won't spend so much time digging into these details, but you can see here a couple of functions on the left, add message and get message, part of the same application. We've set a constant there. And then in each of these, there's some work that's being done. So for adding the message, we're instantiating a new message, and then we push that message onto a collection of posted messages. And when you get a message, we're basically iterating over the list of messages and building up this array of posted messages that we then return to the client. Using the message limit as essentially an upper bound. You can think of it like pagination, 10 messages per page that we return. This is an important aspect, of course, for blockchain technology because any kind of compute and data access costs. And so you don't want unbounded operations in your blockchain dApps. You don't want to do something that could potentially return 1,000 messages because that's going to cost a lot, and it's very unlikely that anybody's going to consume that number of messages. And so you don't want your users paying for that. You don't want to pay for that. And so you want to make sure that you're always constraining your operations to produce what they need to produce and never anymore. And then the Rust side of this, again, same thing. We have the struct with the guest book messages as a vector, and then we have here the interface where you can add messages and get messages. If you're not familiar with Rust, I can point out briefly that the near bindgen that is visible here in the Rust side, and maybe you noticed it over here as well in the data side in assembly script. In Rust, this is a macro that's actually adding some code, boilerplate code that you have to add to every contract. Among that code is we detect if the mutable, the owned mutable reference to add message there, mute self is there, then we know that this method will change the contract state, which it does there by pushing a message onto messages. And so that has some implications about how that runs internally. So you can see immediately by reading the contract interface whether or not it changes the contract state or not, for example, in Rust. In assembly script, you have to actually read the assembly script to get a sense of whether or not it's changing contract state. Regardless of whether or not you're building with assembly script or with Rust, the output is always a WASM file. And WASM has this format, WebAssembly as text, that you can read, and you will see if you read the WebAssembly as text that's emitted by either of these languages when they're compiled to WASM. If you read the WebAssembly as text format, you'll see the names of your methods right in the text actually, and it's quite readable. So here's the add message, and you can see that we have some local data, we're getting some variable, we're calling something internally to retain the value of that, maybe setting some number, and so on. So you can actually read this and sort of make sense of it. The assembly script generated WASM is typically smaller and the WAT is more readable because the compiler is much closer to the WASM format. It's a much simpler tool chain. There's not so much tooling to go through. Whereas with Rust, there's a bigger, more mature, richer tool chain. And so the WAT file is harder to read and the WASM file is typically a little bit bigger. That matters as a blockchain developer because when you deploy the contract, you're going to pay for the amount of storage that you use. Remember, your data is being, your contract is being deployed to a computer that someone else is maintaining for you, and you're paying them. You pay them by paying effectively a kind of rent that we call storage staking. And we can discuss that if anybody's curious. Yeah, great. So a couple of questions, and I see Shreyas is answering them. Keep those coming, no problem at all. Thank you. And so comparing assembly script and Rust here, we've already discussed assembly script is easier for prototyping, while Rust is more battle hardened and mature language. And of course, you can take a look at this list here to get a sense of the differences. If we talk about building, create near app, which I mentioned earlier, this is what it looks like. And so here, you basically, at the command line, you can install create near app as a global tool, or you can use npx to just run it directly. And if you type create npx create near app -- help, you'll see the details of like the different kinds of front end technologies you can use. In this case, it shows vanilla and React, although we've added more recently. And the different kinds of contracts here, languages, assembly script and Rust, which we may add more in the future, but none are slated that I'm aware of. And so these are the differences here, depending on this combination. Again, this list is a little bit bigger for front end. I think we're up to 3 or 4 now that we support because of bounties that people have submitted for other languages, other front-end frameworks. The usual suspects, but I don't want to give away too much because that's one of the scavenger hunt questions later. And so here you can see there's these 4 combinations on basically, it's just a 2x2 grid of JavaScript, React, AssemblyScript, and Rust. And you can see these folders are almost exactly the same in terms of the scaffolding that's being output, just some slight differences in folder naming and file structure, depending on whether or not you're using AssemblyScript or Rust as the backend, and whether or not you're using plain JavaScript or React as your front end. And so in this sense, it's actually very instructive to go and generate each of the possible scaffolds and explore those file systems to see the differences there. Yeah, that's great. Thanks for posting that, Shreyas. Definitely check out the bounties to see if there's any there that you're interested in leaning into. And so in this case here, we can just npx create near app, banana is the name of the application. Immediately we'll see this suggestion for what we can do next. Yarn dev will actually create a new contract account, create a new account, deploy the contract to that account, launch the server so that you can see your web application, a web server, so you can see your web application running against testnet in just a few seconds. So it's the fastest way to get started with a new app, actually. And so here, yarn dev, this is what it does. If you're familiar with node development, this will look obvious to you. Of course, you can poke through some of these details here in the package JSON. This is what you get when it launches. And you can basically sign into your wallet, creating an account if you don't already have one. And then you can edit the greeting and save that to chain. And you'll see that it actually, the change gets applied on chain. You'll see that transaction in the Explorer and sort of verify. You also get this little toast that pops up in the application. And so all of this is available for you to review if you want to include these kinds of behaviors in your own apps. And if you want to dig a little bit deeper, here's some things that you might explore by answering these questions. Where do we set up a connection to Near actually? And if you want some hints, they are there in the lighter colored text. Where do we log in? Which lines of codes connect? Which lines of code connects the contract to the JS context so we can actually call it? And then can you consider sort of reverse engineering, some of this stuff, maybe changing what's happening in the chain, in this case, to reverse a string, for example. And so hopefully this is a good kind of intro. As a reminder, you can learn, build, and earn with Near today, whether you're joining the Open Web Collective, the grants program, checking out the bounties program, Figment Learn pathway for Near that you can start today, or Gitcoin kernel. All of these are opportunities to dive in immediately. And as a reminder, we have the scavenger hunt coming up in just about an hour or two here. I'm not sure exactly what the timing is. And so if you want to come and play with us a little bit, you're more than welcome to do that. You'll find these slides at bit.ly/near-kba. And if you want to join us, please do. Check out near.org/learn. Telegram, Discord, Stack Overflow will be there.